So one thing that you do find is that many operations are kind of a variant of these. For example, if you're doing group by is the same, except now, it's like duplicate removal, except let's say when you do group by, you want to find min, count, max, things like that. So for every distinct value that you keep, you also have to maintain the current minimum for that value, right? So if you group by A, minimum of B, then for each top A value, you keep track. So the first time you see an A value, you keep track of the smallest B you found. And then every time you get a new one, then you keep updating the smallest B until you are finished with all the relation tuples. Only then you know that you are done and you found the correct aggregate. And then you can actually output. So this is an important distinction that you have to remember, right? And keep this in mind for every single operator that we see, whether the operator is blocking or not. So that means that to be able to output even one tuple, if I have to first read all the tuples of the input relation, then that's a blocking operator, right? So that means that to output anything at all, you need to read all input tuples. A good example of this is group by, for example. Group by count. I have seen that you use group by in a strange way in the exam. You basically want to group by everything. You only want to group by unless you only need to group by if you're doing some sort of an aggregation. Otherwise, just use distinct. I think it's easier to read. If you don't have a min-max, group by is the same as distinct. But I think it is actually better to use distinct, in my opinion, so that I can understand what you're doing. Okay, so if none of these do work, then we need to do sorting. So you realize that sorting is like the first algorithm you will ever learn, right? Whenever you take CS1, you learn sorting. But the thing is that sorting is basically the n log n is after you read the data into memory. But for many things where the data does not fit in memory, what can you do? That is the general idea of external sorting. So the general idea is that I have so much data that I can never read it all at once into memory and sort. So, for example, so in many cases, M is much smaller than pages of R. So I cannot really sort everything in memory because I can only read M things at once. As a result, I'm going to do 2 passes. Okay? So first pass, I'm going to sort the relation, but I cannot sort everything. How many pages at once can I sort? M pages, right? So in the first pass, what I'm going to do is I'm going to read the relation into M pages. Okay. So read M pages of R in memory. Once it's in memory, employ your order of n log n algorithm. Let's hope that's as efficient as possible. And shuffle these to sort in memory. Now, this is M pages worth of data, but now they are sorted. So now that they are sorted, but you are not done because it is not all of R, I need to write it to some temporary storage. So read M blocks, sort, and then write it to output. Now you're not done because there are more pages, so read the next n blocks, sort it in memory, write it to output, write it to temporary storage, and then do this for every single page, right? So you're going to do it in basically stages. I cannot sort all of it, I can sort m things. So what would be the cost of this step? So to be able to do this, do I have to read every single page of R? Yes. How can I sort something if I don't read it in memory? And then, since I need those memory blocks to actually do the next thing, I keep shuffling them back to this to free up space. So every single page that I read, I'm also writing it back. So the cost of doing this is 2 times pages of R. So 1 time to read and 1 time to write. Okay. So this is kind of the step 1. Okay. So let's try and see a simple idea. So let's say I have 6 pages in R, and I only have 3 blocks of memory. So right? Suppose this is the contents of 6 pages. If I actually had 6 pages of space, I could read all of it and then sort. But since I don't have 6 pages, the best I can do is I can read these 3 and then sort them among themselves and basically create 3 new disk pages with the same contents but sorted. So 1, 5, 6, 8, 1, 4, 5, 6, 8, 9, 21, 32, and 35, right? It's basically the same amount of information, just sorted. And I'm going to do the same for these. So I'm going to sort these up. Like this. So basically, this is what I did. But what I ended up doing is I read 6 disk pages, and then I wrote 6 disk pages, right? So my total cost so far is reading all of these pages and writing all of these pages. Not overwriting, but writing to a separate place. But I know that these 3 are sorted among themselves, and these 3 are sorted among themselves. So I'm going to call them sorted groups, right? So I basically have 2 sorted groups. Even though it is 6 pages, this is sorted and this is sorted. So if you want to find the smallest, you only have to find the smallest value between these 2 pages. So you can see that given pages of R, I create this many sorted groups in general. Okay. So now the next step is the second pass, which is the merge pass. This is in fact a merge sort algorithm. If you ever implemented merge sort, what you do is you basically divide the data, you sort each individual part, and then you merge them, right? This is the same idea. So since now the data is sorted among themselves, I'm going to merge. So I can only merge m blocks at a time because that's how much data, how much space I have. So what I'm going to do is I'm going to take my m blocks and I'm going to read one block from each of the sorted groups into each, right? So I'm going to read first block of first sorted group. First block of second sorted group. And this is going to be the first block of mth sorted group. Basically find the smallest block from each of the sorted groups, and then from here read the smallest value, remove it, put it in the output. Read the next one, delete it, put it in the output. So now basically do a merge all values and output. And while you're doing that, if a block becomes empty, then read the next block for that sorted group. Okay. So if I can actually finish the sort stage at this point, the total cost of this is really reading every single page one more time. So this would actually have the cost of pages of R. Because I read every single disk page, I do my merge, and then I put it in the output. So when I put it in the output, I'm done. Okay, so let's try to see what happens here. Basically, I'm going to do the same thing here. Now I have 3 blocks, m is equal to 3, the same m that I had before, but I only need 2 because I have 2 sorted groups. So I'm going to use 2 blocks. And I'm going to read the smallest block from each one. So the smallest block for this one is 1, 4, 5, and the smallest block for this one is 2, 3, 10. Then I'm going to find the smallest value, 1, put it in the output. Smallest value 2, put it in the output. Smallest value 3, put it in the output. This is really what's happening as the next operator is asking for get next. Get next means that get me the next sorted tuple, right? So to get the next sorted tuple, I keep reading the smallest value from these. So as I get new tuples, as I get new requests, I read 4 and 5. Now at this stage, this block is now empty. So I can get the next block for the same sorted group. So now I'm going to read here these 3 values, 6, 8, and 9. So now I'm reading the next block. Again, I continue doing the same thing. Find the smallest value, 6, put it here. And then find the smallest value, 8 and 9. Then you are done. Now you read the next block here, which is 21, 32, and 35. Now I finally output 10 here. Now I read the next block of this one, which is 11, 12, and 15. So in fact, I'm going to do 11, 12, and 15, which will get rid of these. And I read the next block, which is 18, 40, 45, and continue, right? So the idea is that I keep reading these, I keep finding the smallest and putting it in the output. Now think of this like two stacks, right? Stacks of plates. They are sorted. So I pick the smallest plate from two stacks, and then do as much as I can merge. If one of them is done, throw it out, get the next one. Look at the data, again find the smallest. When you're done, throw it out, get the next one, until you're done processing both of them, at which point now you have a sorted list. Okay? So, any questions about this? Well, what if the data itself doesn't actually fit in memory in the second pass? It is likely that I cannot do the same thing in the second pass. So let's see an example. So for example, suppose you have (1,000) pages, and I only have 10 blocks. So I cannot really, so let's do step one. Step one says that read data pages 10 blocks at a time, sort and write back, right? So read once, write once. You will basically get 100 sorted groups. And the total cost of doing that is (2,000) pages, because you had to read 1,000 disk pages and you had to write 1,000 disk pages. So you have already spent 2,000 disk page cost, and you really don't have a sorted relation. So in the next step, you want to merge. But to be able to merge, you actually have to read one block from each of the sorted groups. And how many sorted groups I have? I have 100. So if I wanted to sort all of these, I need 100 disk pages, 100 memory blocks. But I still only have 10 memory blocks, so I cannot really read them all and merge. I can only merge 10 of them. Okay? Actually, it's a little bit more, because it's actually, I can only merge 9 of them, plus because I have to use 1 for output, right? So basically, we are going to disregard that for simplicity. But in step 2, I'm going to read 10 blocks, 10 sorted groups, and merge, because m is equal to 10. But since I am not finished sorting the whole relation, I need to store these back on disk. I need to write this output to disk. So I'm actually going to write this to disk. Again, to a temporary stage, right? So, and I'm going to repeat this ten times, because I can merge 10 groups at a time, and I have 100 groups. So I'm going to take the 100 groups, and I'm going to reduce them to 10 sorted groups. So at the end of this, now I have read the relation once, and written it once, and I ended up with 10 sorted groups. So the cost of this stage is also 2,000 pages. now that I have 10 sorted groups, I can actually read them, read 10 sorted groups, and merge, and output. Okay. In the final output stage, as I don't write, all my cost is just reading the relation once. So my cost is 1,000. So the total cost of this case is actually 5,000. Now, one of the nice things about external sort is that it's flexible, right? So suppose that you have lots of other queries operating at the same time, and after you are done with step one, you suddenly have more memory. If you allocate that memory to sort, now the sort can be faster. As a result, maybe you can change the amount of buffer that's available and change the speed. And if you had less memory, it will still process, but it will be slower. So it can grow and shrink based on how much memory you have, which is very useful in like a very dynamic system with lots of memory requirements. So this is kind of assuming that it's always 10 blocks. And 1,000 data pages is not really so outrageous. Even the small IMDb database we had actually had, some of the tables had like 600 pages, for example. So it's not like outrageous. Now, here's my word of advice. If you ever work with large data, do not ever try to read the data into your Python program or even C++. Sort it there and then do work. Unix has external sorting and it's very, very, very fast. So if you actually use Unix sort, have you ever used Unix sort? So yes, so learn about Unix sort, right? So you can do sort minus, you can say sort by the first key and then the second key, something like this. This is external sort. It is extremely fast for large data, much faster than anything you would do with your program. So learn it, love it. External sort is a very different thing. Okay, so it's extremely useful, even outside of databases, as long as you learn how to use it properly. So, all right, you will have to learn how to do this processing and have a mental model of what's happening at each step, right? So basically you have sort, sort in groups, and output, and write to disk. And step 2 is merge in groups, and if done, output. Otherwise, write to disk. So the step 2, you may actually end up repeating many times if you cannot finish it at once. So this can be repeated. And if you're repeating it, that means you have to write the data back. Now, one thing that you realize is that even though you're reading pages in blocks of 10 or blocks of 100, you are still, at the end of the day, you're reading every single data page and you're writing every single data page. Okay? Just try to keep in mind that whenever I tell you how many this pages, it's just that you can never read half of a relation, right, to answer a query or to sort the relation, to sort it. So it's always a multiple of the number of pages in the relation. It is just that how many times is what we are looking for. Now, once the relation is sorted, now your life is great. You can do all sorts of operators after a sorted. So if R is sorted, then a lot of the operations that we talked about becomes very simple. they become almost trivial. Okay? So let's think about duplicate removal, right? So for example, duplicate removal. Basically, you only need one page, and you only have to keep track of the last tuple that you have seen. This happens to be the program that I write like 100 times in CS1, right? You're reading something and then you keep track of whether you have seen a new tuple. Until that, you keep skipping and so on. This is one of the basic things we do. You can do all the same things that we talked about. Things like set union. Now the set union becomes or let's say set intersection. Now this time, you need 2 blocks, one for R, one for S, and then you basically scan this until you find one in common and you output, right? This stage is reminiscent of actually the sorting algorithm, right? This is the merge step of the algorithm. It's almost like a merge step. Yes? No? So in the merge step, what you're doing is you're finding basically the smallest value. Here you're finding the smallest value in both of them. In fact, if you are really implementing this for real performance, you can combine this with the sort algorithm. So what you can do is, you can combine with sort. So for example, you can sort R in M pages and output, sort and write to disk, sort S in M pages and write to disk. Okay. And then in the final stage, what I can do is I can actually implement the merge and the set intersection together. So here I can combine merge and set intersection if I have 2 M pages. So ultimately, these operators have different pieces that you can mix and match. So a lot of the set operators actually don't need the full sorted relation because you can actually combine the merge step with the set operation. Another operator that's very easy to do is group by. So let's say group by and compute min, max, and so on. All you have to do is keep computing the aggregate for the current tuple, right? You sort by, so if you have group by A, then you sort by A. And then all you need is one block where you read one block at a time and keep track of lost tuple and lost A value and aggregates. So again, once it's sorted, you don't need more than one page. So sorting, super useful. It doesn't, you pay the price of sorting it once, but once it's sorted, it helps many operators potentially above the chain. So when you're trying to figure out whether to sort or not, even though sort is costly today, it may help you tomorrow. So you actually, for a moment, keep the sorted relations in as a possible query plan, and then look at it. We will talk about that. All right, so if sorting doesn't work for you, you can also use hashing. Now, sorting is basically sorts the whole relation, whereas hashing will actually be a very different type of query operator, because what hashing will do is it will take your data and divide it into groups, right? So the idea is that you would have one disk page for reading the relation R, and then you're going to hash on some attribute, depending on what you're doing, into m-1 blocks here. So take the tuple, read the tuple, decide on which of these memory blocks it goes, and put it in that block. Do the same thing for this one. If at some point your one of the blocks fill up, it's possible because if your relation doesn't fit in m-1 blocks, then you basically need to, you cannot hash all in memory, right? So this is a multipass. So if you cannot fit in memory, that means once this becomes full, I have to write it to disk. So I'm going to write it to basically think of this as read the relation and then divide it into hopefully m-1 equal groups. But they are not in any way sorted. They are just based on the hash value, right? So whatever you're hashing on, it basically grouped the relation into that many blocks, right? So basically, the initial hashing step is read all of R once, and then write R once. But you are writing it in terms of m-1 hash buckets. So if you have, so basically the cost of doing this so far twice the number of pages because you read once and you wrote once. Okay, so in the unlikely event that all the buckets have the same number of data, right? So if my hash was perfect, if hash distributed tuples equally, then each bucket will have pages of R, this many pages. So if in fact I was able to distribute it evenly, this is how many pages I will have for each bucket. It may or may not be, but if the buckets are small enough to fit in memory, now you can actually do any single operation that you want to do for each bucket separately. So if a bucket fits in memory, meaning m pages, then I can do many things now for each bucket separately. So for example, I can read each bucket and do things like duplicate removal and group by, all within the same bucket. Why? Because if you're doing duplicate removal, then the same a values, the tuples with the same a values will be in the same bucket. So I can just do duplicate removal inside each bucket separately. So hashing looks similar, but in fact it's very different than sorting, because hashing is a divide and conquer method, whereas sorting is basically a uniform over the whole relation, right? So hashing is extremely useful because it is divide and conquer. Divide your relation into smaller groups and then perform the same operation, because now that group is going to be able to fit in memory. It turns out that Postgres uses hashing extensively for many, many operations. So if you were to do things like set union, for example, set union, what you would do is you would basically hash R and S to the same buckets. Then you would perform the set union in each bucket. And you can do the same thing for any other set or bag operation. So you can hash a single relation, you can hash multiple relations, and it's extremely useful. All right, so remember, anytime you're doing this, it's basically about how much memory you have. So let's say you did hashing. After you do hashing, if your bucket doesn't fit in memory, then what you will do is you will probably take that bucket and you will hash it again. And then eventually you have fewer enough values that you can do this, right? But the bigger that your relation gets, the more costly these operations are. And the cost is not really linear, because now you're doing multiple passes over the same relation. So now before we go today, I want to do index search. And then on Thursday, I want to do joins. And then we will start talking about query optimization. But now that you are doing the homework, this should actually be somewhat obvious to you. But we can talk about all the different ways we can now perform these different queries. Okay? And on Thursday, there could be a quiz, which will have all sorts of estimate the cost of this and that kind of thing, basically. Just so that you can start to read this stuff. All right, so anytime you have a selection condition, you can use table scan, which then the cost of this is pages of R. You already know this. You can implement it, and that should be fairly easy to do. Now, if you want to use an index, it all depends on what the index is on. So let's say you have, for example, you have something like this, right? So you can always use table scan to answer this query, and that will return you pages of R cost, okay? And that's always available to you. So let's try to think about what will happen. Suppose I have an index, let's call it I1, on R.A. Now in that case, what I can do is I can scan index I1 to find, and let's see, let's change this to select D, okay? So I can scan I1 to find tuples where R.A is equal to 5, right? So then that means that I can scan I1 for R.A is equal to 5. Now all the tuples that I find here, I have to read from the relation, okay? That means for all the tuples that are matched, read the tuple from the data disk, and check for B and C condition. And then output the attribute. Okay, so the cost of doing this is a little bit tricky, right? Because first you have the cost of reading the index, which will depend on how many tuples there are that match A is equal to 5. That means how many leaf nodes you scan and what's the depth of the tree, right? So you have, some internal nodes and some number of leaf nodes. As many as it would take to read this index. Then, for every tuple matched, you are going to read a data page, right? So then, plus number of tuples matched you're going to read a disk page for every single tuple that is matched. Is it possible that the number of tuples that are matched to your query is greater than the number of pages? Is it possible that I actually read more than number of pages of R? So think about, yes? The tree height is fixed. Why should it depend on tree height?
Well, it's just going to trigger the case where you have one tree, but your tree height is greater than one, so you have to do really.
Oh yeah. Well, I mean, let's say that you have 10,000 tuples, and 5,000 of them actually have A is equal to 5. Then it may turn out that I have to read 5,000 tuples. Even though I have actually, let's say, 500 disk pages, I'm not going to necessarily take all the tuples that I find, sort them by ID, and then read only one at a time. To be able to do that, I actually have the memory to keep all of these tuples that I find in memory and sort it so I can actually read it only once. So generally speaking, that's not really what you would do. You would basically read the tuple, go and read it, read the next tuple, go and read it. So it's possible that you may actually read the same data page multiple times for different tuples. Okay? In the unlikely case that you basically have very few, then this could be very good. So the whole thing that I'm trying to say here is that this could be very large, even greater than pages of R. So the cost of really an index scan is good if the search itself is actually very selective, meaning that it actually only returns a few attributes, a few matching tuples. So if I had the same query, but I have a new index, index I2, but the index is actually sorted as follows. It is on r dot d, a, b, and c. So now to answer the same query, what can I do? This is what you're doing for the homework. What does this take? To be able to answer this, you have to scan every single leaf node, because the index is not sorted by A, right? It's sorted by D. So basically you have to scan one internal node from each level, and every single leaf node. Well, once I scan every single leaf node, find all tuples that satisfy A is equal to 5 and B is equal to 10 and C is equal to 20, and output the D value. I actually never have to read the relation anymore because I'm only interested in attribute D, and that's already in the index. So basically, the previous question, the previous index was not very useful because I could only apply the A value. So that means that it was not very selective on the index, but I could only scan for that A value. So if in fact for a given A value there are very few tuples, this could be great. If there are many A values, this could be bad, right? Because it depends on, after scanning the index, if I still have to read many tuples, this could be bad. The second time, this is actually not very good because it's not at all selective on the index. I have to scan the whole index, and the index is non-trivial because it has 4 attributes. But by scanning the index, I can answer my whole query because it has all the attributes that I need. So even though not selective, this could actually be very useful. Now there is a third possible case. That suppose table R is actually clustered by R dot B. So what that means is that I have a B tree index, and then for a given B value, all the tuples for that B value are stored clustered on this, on few data pages. Remember I talked about primary indices, things that are index sorted tables? This is the general idea. So if R is actually clustered on this, with an index on R dot B, then my algorithm is a little different. First I scan one internal node per level to find the first data page for R dot B equals 10. Okay. So I'm going to scan the index, and then it's going to get me to an actual data page. And in all the data pages, I have all the tuples with b equals 10 with other values, then b equals 11 other values, and so on. Since now this is sorted on this, I can actually just start scanning the table. So scan data pages for r.b equals 10 and find all possible matches to the query. So now what this is doing is it's telling me where to start scanning, and I only have to scan all those tuples that have r.b equals 10 on this, and that's all. So I only have to scan pages of R divided by however many B values there are. Assuming that each one is equally likely. Okay. So indices can be used in 3 separate ways. And this is the important thing to get out of this lecture. Okay. So one is a primary index clustered on some attribute. That basically means that you only have to scan only that part of the relation that satisfies your query, right? So this is the ideal case. If your relation is sorted, you can never beat the speed of this, right? So if you want to really implement this and you know what your queries are, you would cluster your data, or even you will hash your data to different disks on whatever you're going to search for, right? So this is the fastest possible way, because you will only scan data pages relevant to your query. If that does not work, then you would like to find a secondary index that is very selective, right? So secondary but selective index. So what that means is that after you search the index, there's very few tuples to read from the relation, right? So after scanning index, only a few tuples are needed. Okay. Now, if you don't have a selective good index, you may still save something if you have an unselective index, but it actually answers your query, right? If your query is unselective, but actually has all the attributes you read, then that may also be useful. So unselective, so unselective secondary index that has all attributes needed for query. So basically the performance kind of goes down this way, right? So this is kind of the usefulness of index. After we are done with this part, I'm going to talk about database tuning. And the most important part of tuning is to decide if there is a primary index that you want to use. If not, what secondary indices are useful. And after you are done with all this, you actually try to find if there are good unselected indices that can be useful for your database. So with that, I will stop today. And on Thursday, I will talk